So today we are talking about acid-base nomenclature, which just means naming. We're going to talk about acid-base pairing, conjugate acid-base pairing, and we're also going to talk about acid dissociation reactions. Okay, so all of this deals with acid-base chemistry, which will be the next major topic that we'll be looking at. Remember, we spend several weeks on each topic, so we're going to spend a good long time talking about acids and bases. The next 3.5, 4 weeks. Okay. So how do we name acids? You need to know these rules. Okay, make a note. And this file, I need to re-upload it online, but it'll be re-uploaded today. So if you don't want to write this down, it'll be re-uploaded to the course website today. I forgot to update the file this morning. So here are the rules for nomenclature of acids. You have 3 possibilities. You have H plus an anion ending in "ide." You have H plus an anion ending in "ite," I-T-E. And you have H plus an anion ending in "ate," right? Ide, ite, and ate, right? Because those are the 3 suffixes from our polyatomic or monatomic ions, right? Monatomic ions all end in "ide," but there are a couple of polyatomic ions that end in "ide" as well. For instance, cyanide comes to mind. And then polyatomic ions that end in "ite" versus "ate. So for instance, sulfite versus sulfate, right? We need to be able to distinguish between an acid made from sulfite and an acid made from sulfate and an acid made from sulfide, right? So we look at the suffix of the anion and we decide what rule we're going to follow to determine how the name needs to be. So let's look at the ones ending in "ide. Okay, if your anion ends in "ide, you put a hydro prefix, and then X is your anion, and then the suffix is ic acid. So this has the prefix hydro, then X is your anion, and then the suffix is ic acid. So for instance, HBr, the anion there is bromide, right? Because that's H plus, that's Br minus. So the anion is bromide, so therefore the name is hydrobromic acid. If you're looking at H2S, that's H plus, there are 2 of them, and S2 minus, that's sulfide, right? Monatomic ion, so hydrosulfuric acid. And then here's a polyatomic ion, right? CN, that's cyanide. H plus, CN minus, cyanide is the anion, ending in "ide. So that will be hydrocyanic acid. Always has a hydro prefix, always has a ic acid suffix. Okay, that's when the anion of the parent ends in "ide. Okay, so anytime it ends in "ide, you'll have the hydro prefix and you'll have the ic acid suffix. Always, always, always. Whether it's monatomic or polyatomic, if the suffix of the anion is "ide, you'll have a hydro prefix and an ic acid suffix. Is everybody good on this rule? All right, let's look at what happens when our anion ends in "ite. Notice there's no prefix now. We dropped the prefix. There's no prefix whatsoever. Gone, away. We don't look at it anymore. The name is just whatever, right? So there's the anion. And then the suffix is us acid. Okay, so for instance, in HNO2, the anion here is nitrite, right? That ends in "ite. So therefore the name here is nitrous acid. There's no hydro prefix. No hydro prefix. Okay, it's just nitrous acid. You drop the nitrite, you change it to nitrous, and then the suffix, of course, acid. This is H2SO3, right? That's 2 H pluses and SO3 2 minus. That means that that's sulfite, right? Polyatomic ion ending in "ite. Therefore, the name is sulfurous acid. No prefix, no prefix. Just the suffix us acid, us acid. Does this rule make sense? Does this rule make sense? Yes? Have I lost anyone yet? Everybody still with me? Good. All right, the last one is when we have 8 as our suffix for our anion. Right, so here we have HNO3. That's the anion nitrate, right? So that means that the name is nitric acid. Here the anion is sulfate. That means it's sulfuric acid. Again, no hydro prefix. This is where we really have to watch our spelling really, really carefully, right? Because sulfurous acid, sulfuric acid, and hydrosulfuric acid. Boy, those all sound really similar. You've got to watch your spelling very, very, very carefully, okay? Because spelling's what's going to get you if you're not paying attention here. Very similar suffixes, 1 or 2 letter differences, especially between sulfurous and sulfuric, right? And nitrous and nitric. So make sure you're looking at your parent anion. If it ends in ate, it's ic acid, and if it ends in ite, it's us acid. Are we good on these 3 rules? Good on these 3 rules. Just look at the suffix of the anion of the acid, whatever it is. Now, when we name bases, naming bases is no different than rules you already know, okay? So, for instance, potassium hydroxide, ammonia, etc. There are no new rules that we're going to learn for naming common bases. So that's a nice break, right? You don't have to learn any new rules. You only have to learn new rules for acids. So I'm going to give you a second to try these. Give them names. I'll pause the recording, and then we'll go over it. See what we got. So what's the name of HI? Anyone want to share? Hydroiodic acid, right? It's from iodide. H3PO4. Anyone want to guess that one? Phosphoric acid, good. What about the next one? Acetic acid, good. And what about the last one? Chlorous acid, good. Any questions on where these came from? Questions on how we got these? All right, let's go the other way. I've given you the name. You give me the formula for oxalic acid, dichromic acid, perchloric acid, and carbonic acid. Take a second and try these. Let's go over these formula writing problems. Oxalic acid comes from what anion? Oxalate, right. And oxalate is C2O4, 2 minus, right? So that means that the formula is H2C2O4. Crisscross. Dichromic acid comes from what polyatomic ion? Dichromate, right? So that would be H2Cr2O7. If we have forgotten our polyatomic ions, now might be a good time to refresh our memory. Perchloric acid comes from what polyatomic ion? Perchlorate, right? So that's HClO4. And carbonic acid comes from what polyatomic ion? Carbonate, right? So that would be H2CO3. Good. Again, if you've forgotten some of your polyatomic ions, you might want to refresher real quick, because we are going to be using all our polyatomic ions that we were quizzed on at the beginning of the semester. So just a reminder on that. Okay, let's talk about the Bronsted-Lowry acid-base model. All right, this is the Bronsted model. Now, I just want to point out there are 2 main acid-base theories that you'll learn as a chemistry student. You'll learn the Bronsted model and you'll learn the Lewis model, particularly when you take organic. Okay, so for those of you planning to take organic, you're really going to focus on the Lewis model. We're not focusing very heavily on the Lewis model in Gen Chem. We're going to look more at the Bronsted model. Okay, so the Bronsted model says that acids donate H+ and bases accept H+. Okay, acids are donors and bases are acceptors. So acid-base reactions are equilibrium reactions. They go both directions, right? So if we're looking at a particular reaction, we compare before to after to determine who was the acid and who was the base. And so if we're looking at this reaction, we compare before to after. HCl becomes Cl-. So did it donate or accept? to go from here to here. Did you donate H plus or did you accept it? You donate, right? So this is the donate. That means it's the acid. And H2O becomes H3O plus. How do you get from here to here? Donate or accept? Accept, right. And if you accept, that means you're the base. And then let's do this one to go from NH3 to NH4 plus. Do you donate or accept? You have to accept, right? So that makes you the base. And here to go from H2O to OH minus, what does that make you? The donor, right? So that makes you the acid. Now I just want to point this out. Look here, right? Here acid is, here water is acting as a base. Here water is acting as an acid, right? This means that it is amphiprotic. That means it can act as acid or base. Okay, so amphiprotic things can act as either acids or bases depending on what they're being combined with. So water here is acting as a base, water here is acting as an acid. It can go either way, right? You can have water act like a base, you can have water act like an acid. We call that word amphiprotic or amphoteric. So just some vocab for you. All right, so according to the Bronsted model, acids donate, bases accept. So let's go through this one again, just real quickly. H2SO4, is it donating or accepting? Donating, so that makes it the acid, and this is the base, right? Because to go from here to here, you got to accept. Oops. And then to go from here, that's the same thing as ClO minus, by the way. Is that a donor or an acceptor? It's accepting, right? So what does that make it? And what does that make water here? Acid, good. All right, I'll pause it and give you a second to try this one on your own. All right, let's look at the answer. All right, so NH4 plus is it's the donor, right? So what does that make it? And water is the base, it accepted. Okay, let's talk about conjugate acid-base pairs. Conjugate base is everything that's remaining of the acid after it donates. And conjugate acid is what we get when the base accepts. So in other words, this is an equilibrium reaction, right? Going both directions. You need to have an acid and a base on the left. You need to have an acid and a base on the right. So that if you're going this way, you have an acid and a base. And if you're going this way, you have an acid and a base. Okay? So the definitions are wordier than they really are in practicality, right? Base is everything that's left over of the acid. So in other words, if you're an acid on one side, you're a conjugate base on the other, right? And if you're a base on one side, you're a conjugate acid on the other. So if we're doing this problem, which we just identified, right? NH4 going to NH3 makes it that's the acid. And so that makes this the conjugate base. And so if this is the base, that makes this the conjugate acid. Right? So if you're going left to right or right to left, you always have an acid and you always have a base, right? Because this is reversible, we need to have an acid and a base on the left, we need to have an acid and a base on the right. Okay, so that no matter which way you're going, you still have an acid and a base. If you're an acid on one side, you're a conjugate base on the other. If you're a base on one side, you're a conjugate acid on the other. So just some, like I said, the definition's a lot wordier than it is in practicality. If you understand the concept, the definition's a lot wordier than it really needs to be. Right? So acid, conjugate base, base, conjugate acid. Right? The only difference between them is removal or addition of the H plus. Make sense? Make sense? Okay, so we just did one with NH3. Let's do another one. Here we go. Take a second and try this one on your own. Let's go over these. Did I turn it back on? Yes, I did. All right, so the acid here and the conjugate base, do we agree? And the base here and the conjugate acid. Again, they are pairs, right? If you're an acid on this side, you're a conjugate base on this side, and if you're a base on this side, you're a conjugate acid on this side. Do we all agree how to do this? All right, and then again, just check your work. Why don't you try this one? I've given you the acid. You tell me what its conjugate base is. See what you can figure it out. I've given you the acid. You figure out what its conjugate base is. And keep in mind, there may or may not be charges involved as well. So see if you can figure this one out. All right, so to turn an acid into its conjugate base, what do you do? Are you going to add H plus to this formula, or are you going to remove H plus from this formula? You're going to remove it, right? So when I turn this into a conjugate base, will it have a charge? Yes, it will, right? We're removing H plus. So therefore, if this is the acid, when I take away one of those hydrogens and I take away its charge as well, that gives me HCO3 minus. Do we agree? What will the conjugate base of H3PO4 be? Number of hydrogens is going to go down or up? Down. And what's going to happen to the charge? Go down or up? Down. We've removed positive, right? So H2PO4 minus. What about HPO4 2 minus? What will its conjugate base be? Right, it'd just be phosphate. What would the conjugate base of NH4 plus be? NH3, good. And what would the conjugate base of water be? OH minus, hydroxide, good. So everyone see how you turn an acid into its conjugate base? Because an acid donates H plus, so therefore you would remove H plus from the formula. Take away the hydrogen and also reduce the charge by 1. Go the other way. This time I've given you a base, and you figure out what the formula of the conjugate acid is. I'll pause the video and give you a chance to try this. All right, let's go over this one. So to turn a base into a conjugate acid, what are we doing now? Bases do what? Accept or donate? Accept. And so since they're accepting H plus, what do I do to the formula? You add an H, and what do you do to the charge? Increase it by 1, right? So we're adding H plus, so this will be HSO4 minus, right? Adding an H, charge goes up by 1. What will the conjugate acid of this be? H2CO3, good. What about NH2 minus? Just NH3. What about ClO2 minus? HClO2. And what about H2PO4 minus? H3PO4, good. Does everybody understand how to take a base and turn it into a conjugate acid? Or vice versa, take an acid and turn it into a conjugate base? Yes? Okay, we've done enough of this, so let's just skip that. Now, one of the things that you'll see thrown around in your textbook and in homework, and we're going to do this in the lab, is an acidic proton. What does it mean to be an acidic proton? An acidic proton is a proton, in other words, an H plus, that is removable. Okay, so to be a Bronsted acid, you have to have H plus that can be yanked off. Okay, and then to be a base, you have to have a place for that to go, for that H plus that you accept. It has to have somewhere to go. So in other words, you have to have a pair of non-bonding electrons, right? If HCl is donating this H plus, it's got to have somewhere to land, right? So you need to have a lone pair to accept it, right? And you've got to have a proton that you could remove. So you've got to have both. You have to be an acid, you have to have an acidic proton. Acidic just means removable, okay, because not every H is going to be acidic. Okay, so here's some examples. Well, actually, we'll skip to the definition. Do I have some? Yes, here's a good example. All right, so this is acetic acid, right? Now notice this is the only acidic hydrogen, this one right here. These 3 hydrogens are on a carbon. They're not going anywhere, okay? It's this hydrogen right here. So even though there are technically 1, 2, 3, 4 hydrogens here, only one of them is acidic. This one's not going to be donatable. This one's not going to be donatable. This one's not going to be donatable, right? Because this is acetate right here, and this is the hydrogen that's getting donated, okay? So just so you know. Now let's talk about a couple other vocab terms. Monoprotic, prefix mon should tell you kind of what that means. Mon, one proton, right? So a monoprotic acid has 1 acidic proton. Diprotic acids will have 2 acidic protons, and triprotic acids would have 3 acidic protons. And once we start talking about equilibrium, which you know that's where this is going, right? The equilibrium value for pulling off the first hydrogen is going to be different than the equilibrium constant for pulling off the second one, and the equilibrium constant for pulling off the third one, right? So because we have, say in a triprotic acid, you've got 3 protons, you can pull them off. You're not yanking them all 3 off at once, right? You pull off one, and it's got its own K value. You pull off the second one, it'll have its own K value. You pull off the third one, it'll have its own K value, okay? And the same thing will work with diprotic. Now, monoprotic, it'll only have 1 K value because there's only 1. Monoprotic, 1 acidic, diprotic, 2 acidic, triprotic, 3 acidic. Okay, so you understand what this vocab means? Everybody good on that terminology? So here's some pictures. Now, oxyacid, don't let that freak you out. It sounds scarier than it is. Okay, so in an oxyacid, that just means that the acidic proton is attached to an oxygen. All right, so here's sulfuric acid. Right? So this one, is it monoprotic, diprotic, triprotic, what? That would be diprotic, right? Because you could take off this first one and have HSO4 minus, and then you could take off the second one and have sulfate, right? And notice the hydrogen is on an oxygen. That's what makes it oxyacid. Here's acetic acid, monoprotic, diprotic, or triprotic. I've already told you the answer, but you can look at the formula too. It's monoprotic, right? This is the only hydrogen that's removable. These are not going anywhere. That's part of acetate, and it's an oxyacid. And then there's H3PO4. What would you predict that one to be? H3PO4. That one's triprotic. Now that third one's really hard to pull off. We'll talk about equilibrium values later. But that third one's got a Ka value that's pretty low. And we've already talked about this. Amphoteric, meaning it can act as either an acid or base. And water is a very common amphoteric substance. And you might see it called amphoteric or amphiprotic. Those words are synonyms, depending on which textbook you're looking at. So there's an example of water acting as a base. Right? And there's a picture of water acting as an acid. Now here is something you need to put in your notes with like stars and exclamation marks and whatever highlighter. Okay? You must know the general reaction for what happens when an acid reacts with water. Okay, when I take my acid and I dump it into water. Here's my acid. Water's going to be acting as the base, right? So A just stands for anion, whatever the anion is. Okay, that's just what A stands for. It's not like, ha ha, this is so funny. A is the anion, okay? So HA, whatever the anion is being combined with water to give me the hydronium ion and the anion, okay? Remember, what does an acid do? It donates. That's why I get H3O+. What's left over is my anion. That's the conjugate base. You must know this formula. Okay? You must know the general reaction for an acid and water. Again, break out your highlighters, magic markers, whatever you want to do. Put big note. You must know this. You have to have this general formula imprinted in your brain. It will become imprinted in your brain because you're going to do it so many times. But the sooner you get it there, the easier life will be. You must know the generic formula for an acid with water. acid plus water. Now notice this is an L. So when I write an equilibrium expression, because you know I'm gonna, right? That's the equilibrium. Is this gonna show up in my equilibrium expression? Right? Because water's a liquid. It's not participating in the equilibrium. Okay, so here's HCl, for example. HCl and water making my anion and my hydronium ion. Okay, that's a picture from my textbook. Now this is something you need to know as well. This can be reactant or product favored, right? Any equilibrium can be reactant favored or product favored, right? So we can have equilibrium lying on this side. We can have equilibrium lying on this side, right? Just like any equilibrium. You can have equilibrium to the products, oops, or the reactants, right? And if it's reactant favored, we say that it is a weak acid. Must know that. If it's reactant favored, we call it a weak acid. What would the K value be? Greater than 1, less than 1, equal to 1. Less than 1, right? And if it's a strong acid, that means that it's product favored. K value greater than, less than, or equal to 1. Greater than, right? So the definition of strong and weak acid, okay, comes from the K values. So here's an example of a strong acid. HCl is a strong acid. Okay, it's a really strong acid. K is significantly greater than 1. This is going to be 100% this and 0% this at equilibrium. I mean, it's a strong acid. Okay. And then here would be a weak acid. Equilibrium is going to lie on this side. You're going to have mostly this, very, very, very little this. Okay. So how do I define a strong acid versus a weak acid? It isn't because one's dangerous and one's safe or anything like that. It's because of the K value. And so we use Ka when we're talking about an acid, right? That's what the little A stands for. We're not just using regular old K anymore. We're talking about acids here. We'll say it's a Ka because it's an acid. Okay, Ka. So the Ka, remember, this is our generic reaction where we can plug in any anion we want. Ka will be the concentration of the anion times the concentration of hydronium over the concentration of my acid. Again, these are all the equilibrium values, not the initial values, right? These are all the equilibrium values. So I'm going to have to make an ice table, figure out what my values are, plug them in. Okay? How come there's no H2O represented here? Because it's a liquid, right? Now I say I'm going to have to make an ice table, and that's true half the time. I'll show you what I mean by that in just a second. So let's just practice here. Write the equation for the reaction of hydrofluoric acid with water, and then write the expression for Ka. So let's do this one together. See if I can move that down. There we go. Hydrofluoric acid has what formula? HF, right. And what state of matter? Solid, liquid, gas, aqueous. What state of matter will that be? Aqueous. All right, when it dissociates, it's combining with water. What state of matter is water? Solid, liquid, gas, aqueous. Liquid. So that is in equilibrium with what? When this donates to this, what am I going to get? What's the conjugate acid of water? H3O plus AQ. And what's going to be the conjugate base here? What's going to be left over? Fluoride. Is it F? Do I just leave it like that? F minus, right. It's fluoride. Okay, so the Ka expression, therefore, would be what? Concentration of H3O plus times the concentration of fluoride over the concentration of HF, right? Does everyone see how we did that? So like I said, if you memorize the generic formula, you can plug in any anion and you're off to the races, right? Is everybody good on how we did this? Any questions on how we did this? All right. If I'm going too fast, please speak up. All right, so there's the answer. Does it matter if you put F minus first or H3O plus first? Is 2 times 3 different from 3 times 2? Okay, you try these. I've given you the acid, and I want you to write its reaction and then write an expression for Ka. So I'll pause the recording, and you try these. All right, let's go over this one. So we've got some acids here. We need to write the reaction, and then we need to write our Ka expressions. So hydrobromic acid is HBr. It's going to be combined with water. What am I going to get? H3O plus AQ plus what? Br minus, right? Don't forget that charge. Can't forget the charge. It's not the same to write Br as it is to write Br minus. And so Ka would be concentration of H3O plus times the concentration of Br minus over the concentration of HBr. Do we agree? What's the formula for acetic acid? Okay, so you can write that as CH, oops. You can write it as H2, C2H3O2, right? You could also write it as CH3CO2, and then you could put the H at the front or the H at the end. Where do you prefer to put it? If you write it like this, where'd you put it? At the end? That's fine. Because, I mean, this more accurately reflects the Lewis structure, because the Lewis structure looks like that. And there's your acidic hydrogen. So this more accurately reflects the Lewis structure. But some textbooks put acetate as C2H3O2 minus. So I don't really care which way you do it. Makes no difference to me. Okay, AQ plus H2O, liquid, is in equilibrium. It's still going to be H3O plus here. Now, if you wrote it this way, acetate would be C2H3O2 minus. And if you wrote it this way, it'd be CH3CO2 minus. Again, I don't care which way you write acetate. Makes no difference to me. A lot of students prefer to write it this way, but this way more accurately reflects what the Lewis structure looks like, so I don't care. Makes no difference to me. So Ka, H3O plus, C2H3O2 minus, HC2H3O2, and you can substitute this in right for here and this in for here. Yes, we wrote it all out. Okay, this is the anilinium ion. So this is C6H5NH3 plus AQ plus water. What are you going to get? H3O plus. I heard someone start saying it. C6 what? H5 NH2. Right. Because when this donates an H plus, that's how you get H3O plus, and then you get aniline. Aniline is an organic molecule. Looks like that. Okay. So the Ka would be C6H5NH2 H3O plus over C6H5NH3 plus. If you understand this concept and the calculations that we're going to be doing with this, you're going to thank yourself so much when you get to organic. I mean, it's just going to make life so much easier because KAs have such a humongous role to play in organic chem. I mean, all the equilibrium that we're going to do with acids and bases is just going to come screaming back at you in organic 1. I mean, I'm not lying. I'm just telling you, it's a big part of organic reactions. And so if this makes sense to you now, hang on to that. Don't forget it because you're going to need it in organic as well. The strength of acids and how the acids, KAs, play into all the organic reactions you'll learn. You're going to be thanking yourself. If this makes sense to you now, please don't forget it, especially if you're planning on taking organic. What's the ammonium ion? It's what? In what formula? NH4 plus AQ plus H2O liquid is in equilibrium with H3O plus what? What's the conjugate base? NH3. Right, so Ka will be H3O plus and H3 and H4 plus. Do we agree on how we did these? If you made a mistake, you see you made it. All right. So, like I said, taking the name of the acid, writing the generic reaction of it with water, and then turning that into a Ka expression, all comes from just knowing what's the general reaction with an acid and water. And if you know that general formula, you can substitute any anion in there you want. Okay? And so the strength of an acid is defined by its Ka. Put this in your notes with like stars and happy faces and highlighter, okay? If Ka is greater than 1, we have a strong acid. If Ka is less than 1, we have a weak acid. This is how we are defining strong and weak acids. It's by their Ka values, okay? It's not because one's safe and one's dangerous. No, that's not how we're defining strong and weak acids. We're defining it by the percent dissociation. How far does this equilibrium go? Is the equilibrium on the reactants, or is the equilibrium on the products? Okay? If the equilibrium's on the products, we call it a strong acid. If the equilibrium's on the reactants, we call it a weak acid. Need to know that. Need to know it. Need to know it. I can't emphasize that enough. And so, I believe I have a list of common strong acids here. Oh, it's coming up. So I'm just re-emphasizing what I just said. If it's a strong acid, you have a big value for Ka. I mean, we're talking big values, like, 35, okay? Extremely product favored. And when we're talking about a strong acid, we're assuming that at equilibrium, it's 100% here and 0% here if it's a strong acid. And then if it's a weak acid, has a small value of Ka, we're assuming that it's virtually all here and very little over here. So let's fill out this table together, just to drive it all home. All right, if it's a strong acid, Ka, greater than 1, less than 1, equal to 1, what? Greater than 1, and it's usually much, much greater than 1. And then for weak acid, it would be less than 1. And again, it's usually much, much less than 1. It's usually, a very, very small number. Equilibrium position, reactants or products for strong acid? Products. And then equilibrium position for a weak acid would be reactants. And then percent dissociation. So in other words, of my original acid, it's 100% dissociated. Right? In other words, it's all H3O plus and A minus, right? And then for a weak acid, it's very little dissociated right? I say very little because there's going to be some product. It's mostly what? HA and H2O, which H2O doesn't contribute to equilibrium, so it's mostly HA, right? So this information, just summarize it somewhere in your notes. It's going to be really, really useful for you to have. Here's your list of common strong acids you need to memorize. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric. And just note that sulfuric is diprotic. Chloric and perchloric. Okay? I think this list is posted on the course website as well. I'm pretty sure it is. But just so you know, you got to memorize this list. So if you can memorize these 1, 2, 3, 4, 5, 6, 7 acids, then that means anything that's not on this list is a weak acid, right? If it's not on this list, it must be a weak acid, right? Or a base, right? Worry about bases later, right? If it's not on this list and it's an acid, it's got to be weak. So if you can just memorize the 7 that are strong, then all the other zillion acids you can come up with are going to be treated like weak acids. And then here are your strong bases, okay? Those 3. So that means if it's a base and it's not on this list, we're treating it like a weak base. Okay, we'll deal with weak bases when we get into KB. Okay, so let's do these verbally. What's the name of HClO? Anyone? Well, what's the name of ClO minus? Hypochlorite, so that would be hypochlorous acid, right? Because hypo is part of the prefix of the base, of the anion, so that'd be hypochlorous acid. Strong or weak? It's weak, right? HNO3, what's the name of that? Nitric acid, strong or weak? That one's strong. H2Cr2O7, what's the name of that? Dichromic acid, strong or weak? It's weak. And then HClO4, what's the name of that? What? Perchloric? Is that what you said? Yeah, perchloric acid, because ClO4 minus is perchlorate, right? So that would be perchloric acid. And that one's strong. Okay, so again, if you just memorize your list of strong acids, anything that's not on that list is a strong acid, a weak acid. Okay, for nitrous acid, write the dissociation and Ka, and then would you expect the Ka to be less than 1 or greater than 1? We're running short on time, so we can just do this one together. What is the formula for nitrous acid? Nitrous comes from what anion? Nitrite, right? Nitrous comes from nitrite. Boy, I've got just 2 duds in a row. I want to find a good one. So that's NO2 minus, right? So nitrous acid would be HNO2. Do we agree? Yes? Okay, so let's write our equilibrium expression. HNO2 AQ plus H2O is in equilibrium with H3O plus what? NO2 minus, right? Can't forget our conjugate base. There's a good marker. And then Ka would be H3O plus NO2 minus over HNO2. Now, are we predicting this Ka value to be greater than or less than 1? Is this a strong acid or a weak acid? I'll tell you, it's not strong. It's not on the list of strong acids. So what is it? It's a weak acid. So Ka will be what? Less than 1, and at equilibrium, Mostly what? Reactants or products? Mostly reactants, right. So the way we do calculations for strong acids are going to be different than the way we do calculations for weak acids. For strong acids, we are assuming it's 100% over here. So guess what? No ice table. Yay! For a weak acid, it's mostly over here, but there's some over here. So we are going to have to do an ice table for a weak acid. So just a preview of things to come. On Friday, we'll talk about calculations for strong acids, no ice table. And then Monday, we'll do calculations for weak acids. Any questions for me before we stop? All right, that's where we'll end for today. Have a good day, and I'll see you.